सर को दे दूं ये मैम को सबको
AICTE Training and Learning Academy sponsored faculty development program on 5G mobile network, technologies, application, and research perspectives. I extend a special and respectful welcome to our guest of honor, Dr. Sam Darshi, Associate Professor, IIT Ropar, our respected Principal Sir, Professor Dharmendra Saini, our respected Vice Principal, Dean Academic, Head of the Department of Electronics and Communication Engineering, and Coordinator of this FDP, Professor Kirti Gupta, our esteemed Dean Administration, Professor Prakhar Priyadarshi, all respected heads of the department, deans, faculty members, and dear participants. To mark the auspicious occasion, the beginning of this FDP is with the blessings of Goddess Saraswati, the embodiment of wisdom and knowledge. We shall now proceed with the ceremonial lamp lighting. May I now request our esteemed guest, Dr. Sham Darsi, along with our respected principal, the vice principal, and dean academic, dean administration, and Professor Surjit Ballara, co-coordinator of the FDP, to kindly come forward for the lamp lighting ceremony. I request you all to please join us for lamp lighting ceremony.
नहीं है जब ये करना
I request everyone to please kindly rise for the lamp lighting ceremony. Thank you. Now I request all the dignitaries and everyone to kindly take their seats. Now we would like to welcome our guest of honor by presenting the token of appreciation. May I now request Professor Dharmendra Saini, our principal, to kindly present a token of appreciation to our honorable guest, Dr. Sam Darshi. Thank you, sir, for graciously accepting our invitation and in honoring us with your gracious presence. Atal Academy is a prestigious initiative of the All India Council for Technical Education, dedicated to enhancing the quality of technical education by empowering faculty members through continuous learning, skill enhancement, and knowledge sharing. This FDP aims to provide participants with comprehensive insights into the latest development in 5G communication technologies, their practical applications, emerging research opportunities, and future technological directions. We are privileged to have eminent academicians and researchers, scientists, industry experts who will be presenting and sharing their valuable knowledge and experiences throughout this program. To formally welcome everyone and to give the outline of the objective of this FDP, I now have privilege of inviting Professor Kirti Gupta, Head of the Department of Electronics and Communication Engineering and coordinator of this FDP, to deliver the welcome address and opening remark. Ma'am, may I request you to please join us?
Good morning, everyone. A warm welcome to Dr. Sam, Associate Professor from IIT Roper, Principal Sir, all HODs, Deans, faculty members, and all my participants. It is a privilege to have you all on this inauguration ceremony of 6 days AICTE Atal FDP program on 5G mobile networks, technologies, applications, and research perspectives. At the onset of this inauguration ceremony, I would first of all like to thank AICTE for giving us this opportunity so that we can learn, we can take this wonderful opportunity forward and take the advantage of this opportunity to learn, explore, and collaborate in the field of 5G mobile networks. So this FDP is witnessing the participants from diverse field, diverse specification. So I appreciate your interest in 5G mobile networks. And let me give you some facts why we have organized this FDP on this topic, emerging topic of 5G mobile networks. So all of you, as you know, and you must be aware that India is now emerging as the fastest growing 5G mobile market. There is a huge expansion in 5G infrastructure in India, and you won't believe that more than 4.7 lakhs base stations are installed in India, and around about 99% of Indian districts are covered by 5G services that are extended in the urban, suburban, and rural areas. It is expected, and the figure is very much eye-opening. It is expected by end of 2028, India will be having around about 770 million subscribers for 5G network usage, and it is estimated that over 40 GB of data monthly will be used by per user. So this is what is the potential in this field and how we are going to cater that. We are going to cater that by bringing AI, again AI, into the network design of mobile networks. That AI enabled network design will be predicting maintenance, network optimization, your customer support, fault detection. So all these will be AI enabled in this 5G networks. And moreover, these will be extended to sectors like manufacturing, airports, healthcare, and education system also. Lastly, this 5G will be transitioning into 5G advanced and then 6G for your future work. So this is the potential of the 5G mobile network, the area in which we will be doing this FDP. And with this, in this FDP, we have many of the avid researchers from all over India have joined hands to deliver you the best of 5G that is available, 5G knowledge that is available with it. So this 6-day faculty development program will be having 2 sessions daily, in the morning and in the afternoon sessions. In the morning sessions, we will have discussions on the expert area of the expert, that is guest that is with us. And then it will be followed by the article discussion. Later in the afternoon session, we will be having hands-on discussion and a case study discussion at the end. Daily, we are going to have that thing. And daily, to make all of you understand each and everything of what is being told to you, AICTE has designed that daily you will be writing or pen downing your learning outcomes for every session. So daily you have to write down and submit it to us. What are your key learnings for this session, for the sessions, both for practical and both for theory and the theory. On day 5, that is on Friday, we have arranged a visit to the 5G use case lab that is in Department of Electronics and Communication Engineering in Delhi Technological University. And on the last day, we will be having an MCQ test, and you will be performing your performance will be evaluated on that basis. So this is all is what is the format that is given by AICTE, and I think all of you are aware of that. So I hope you will all will be having the good learning in this field, 5G mobile networks. So have happy learning. Thank you. Thank you for joining. Thanks.
It's been. I was thinking that I was the first one who will be planning. No, no, just keep it.
So it's recording. That's why. So that. So it's on.
Hello. On behalf of the family, hello. Is it all done? Okay. On behalf of Bharati Vidyapeeth family, I welcome Sam Darshi sir. That it took time for us from his busy schedule, and we wholeheartedly welcome you, sir, on this campus, and all head of departments, deans, faculty members from inside and faculty members from outside. It's always a pleasure to be part of such event where faculty members, talk about learning. All the time they are in the classrooms and delivering their knowledge to the students. Now it is the time to update themselves, ourselves. We see that AI is around us. We know that in the classrooms, if we are not delivering up to the expectation of the students, up to the expectation of the industry, then I don't think that we deserve to be called as a teacher. So to cater to or to come up to the expectation of industry and to the students, we need to upgrade ourselves. And for that, such programs are always mandatory. I was in a seminar, whole day seminar, where it was talked about that with the advent of AI, what will be the future in the classrooms, outside the classrooms for the students. We all know that jobs are going away for the students, those who are coming out of this BTech programs and all other professional programs. And there are sectors where the jobs are being created. So when this such transformation is happening around us, so it becomes our duty or the duty of the teachers to upgrade ourselves to this transforming world or to meet such challenges where jobs are going in one sector and are being created in other sectors. So we should be ready to give such transformative knowledge to our students. Only then I think in the future we'll be able to survive and our students will get the good amount of knowledge from all of us. So that is the duty of all of us. So I would request all of you to focus on the new research and innovations happening in 5G mobile networking and how AI is being applied. And AI is all around us. Whether you take your mobile, car, home, and all equipments which you are operating, they all are operated on by means of AI. Some part of AI is always involved. So happy learning to all of you. I don't have much time today. So best of luck and happy learning to all of you. And thank you very much, sir, again. And thanks to the EC department for organizing this. Thank you so much. And again, in the last, I would thank you to AICTE for giving us opportunity for organizing this FDP program for our faculty members and the faculty members around us. Thank you so much.
The success of any ability lies in the quality of knowledge shared by its distinguished experts. We are privileged to begin this academic journey with an eminent researcher and academician from one of the India's premier institute. It is now my honor to introduce our first resource person for today's inaugural technical session, Dr. Sam Darshi. Dr. Sam Darshi is an associate professor in the Department of Electrical Engineering or at the Indian Institute of Technology, Ropar. He obtained his BTech honors in Electronics and Communication Engineering from MJP Rohilkhand University, Bareilly, and earned his PhD from the Department of Electronics and Electrical Engineering, IIT Guwahati. Dr. Darshi is a senior member of IEEE and has made significant contributions in the field of modern wireless communication. His research interests include next generation multiple access techniques, advanced underwater networks, cross-layer network design, and intelligent, and intelligent transportation system. His research has been published in reputed international journals and conferences. He continues to contribute actively to emerging communication technologies. Today, Dr. Darshi will deliver a technical session on the topic from ARQ to intelligent retransmissions in 5G and beyond. In this session, participants will explore the evolution of retransmission techniques in wireless communication, beginning with automatic repeat request and processing towards intelligent retransmission mechanisms designed for modern 5G and future 6G networks. The session will also provide insight into advanced multiple access techniques, including rate splitting multiple access and hybrid automatic repeat request, highlighting their roles in improving reliability, spectral efficiency, and overall network performance. I'm sure this session will provide valuable insight into one of the most exciting and rapidly evolving areas of wireless communication. May I now request Dr. Darshi to kindly take over the proceedings and deliver his inaugural technical session. Please join me in welcoming Dr. Darshi with a warm round of applause.
तो नहीं करना है आप बस यही
Please follow by ये नहीं देना
points of 5 friends like the base and this reminds us that world is actually very small. Friends, we often be friends of friends of friends. There is nothing but a multi of communication. You will be a today's topic, keeping the diverse audience. What I planned, obviously, I need to keep the content aligned with the theme of the workshop of this lecture. So I will not be presenting complex maths, but I planned the session in such a way that those who are not well aware about the topic, they will also get to realize what is 5G, what are the requirements, why we are discussing this topic, what is the need, why the existing technologies are not sufficient to deliver. This all we will discuss. So we'll first make a brief background. So, start. Okay. Okay. Some message appearing on the screen. Yes. So our Indian tradition is first to go for Guru Vandana, and for technical world, I believe Google is the god. But I think I should update the slides. I should add ChatGPT and Gemini and Cloud also in this. Yeah. So why this thing is not working somehow. Yeah. Now it's working. So before going into the technical thing, first I would like to give you a brief overview of scenario where this topic is it lot of echo? I should keep it at distance. So first I would like to show you some of the scenario. Fine. इसमें तो echo बहुत है. There are lots of multipath actually, and they probably is making destructive interference at this point. So should I remove this? इसको हट. Okay. So I would like to show some of the real life scenario also, so that you get the idea where these things will be applicable. Because see, that era is gone when we do some research on paper and some equations we have derived. Nobody is interested in that, not even government. They also ask you to, take your research out from paper and to bring to the lab or to the ground, so that eventually some product or some usefulness of that research may come out. So for that, it is very necessary that you should have a feel what you are doing, why we are doing, and how you are doing. Often I see in BTP or MTPs, BTech projects, students do some project because guide has told why they are doing. So they have only one motive, because it gives them grade. There is no other motivation, right? While there should be a technical or more broad motivation what you are doing, right? So for that, this scenario, as I said, this is multiple access technology. So technically, this is when there are multiple users, right? Lots of users are accessing certain service. So this figure primarily is, intelligent army of many things. Intelligent in the sense, nowadays more or less everything is intelligent in some way. As we just heard that more or less there is some role of AI everywhere. So everything has some intelligence. But now, how we can exploit that intelligence or how we can make best out of it, that is what the prime requirement. And why suddenly everyone is talking about maximum utilization of resources? Why there is a need to have, first of all, intelligent things, and how we can utilize the intelligence of those things? That is the question of the hour that we will see. So some other use case scenarios are, this is one scenario where you can see this is a post-disaster scenario where rescue team members are actually performing the rescue operation with the help of some drones. So there are lots of drones running around, and the drones collect some data and then they provide to the rescue team members for the needful action. So here you can see there are lots of users in terms of drone or in terms of rescue team members who are actually collaborating to perform certain actions, right? Or this is another example of a smart home where lots of gadgets are actually communicating with the cloud. So there are lots of multi-users. They are getting instructions, control commands from the cloud for the optimum performance. This is another scenario of a typical city where, let's say, there is some main central tower, and then there are other homes which have small base station, or you can say pico base stations, and then users are connected with them either through multipath, through multiple hops, or through single hops. So there are again multi-users are involved in the picture. Or this is another scenario where, though this is yet to come to the ground in full capacity, but everyone is aware about this, wireless body area network, where we have a lots of sensors on body, and they are sending data to some on-body access point, and that access point is sending data to some other control station or some other user. Now here, since there are lots of sensors are there, you can consider this as a scenario of आप में से कोई इधर हो जाए, मुझे लग रहा है शायद डायरेक्ट कम्युनिकेशन का इशू हो रहा है. Not very sure. या शायद मुझे थोड़ा और पास होना चाहिए इसके. हाँ चलो ठीक है, ओके फाइन. या इस तरफ रख दें तो बेहतर है. आ जाएगा इधर. पेन भी. So here also you can see those networks may be getting interference from nearby sensors or some other gadgets. So that is again another scenario. And this is another typical network where satellite communication is there. Satellites are communicating with drones. Drones are communicating with vehicles. Vehicles are communicating with pedestrians. So in a way, V2P, V2V, V2S, or broadly V2X scenario is there. What is RSMA will come, but that is one of the RSMA based network. We'll discuss what is RSMA. This is another scenario where satellite is actually communicating with lots of users in the ground. They are segregated, divided into different small clusters. And so this is again another scenario of multi-user. This is another satellite based communication. So these are some of the ground scenario where this talk is applicable. Now, once we have a rough idea of the scenario where these things are applicable, now let's discuss why is this needed to discuss all this, right? We already, our 3G, 4G is running like anything. I mean, all the existing techniques are there related to either of the layer, be it a physical layer or a data link layer or a transport layer or a presentation layer. Then why there is a sudden need to redesign or relook at the requirement? So let's connect it with the 5G. Actually, this requirement came primarily because of the strict requirements that 5G talks about. These are the three pillars on which 5G is based, which is those who work in wireless communication are well aware that it promises to deliver enhanced mobile broadband, ultra reliable low latency communication, and massive machine type communication. Now, this actually forces us to redesign or relook to the existing methods that we have. When we say ultra reliable low latency communication, latency, we are talking about less than 1 millisecond, and ultra reliability, where we say some 99.9939 of reliability. Can you imagine how much degree of freedom now you have once I say 99.999% reliability I need? I mean, almost zero. I mean, there is no scope of error. It is similar to the fact that I mean, you deliver the services at 95% reliability also, and you are delivering at 99.39 of 39% also. Then what's the difference? The difference is, let's say BCCI says I need World Cup. Fine, even if one of the match you lose doesn't matter as far as it is not quarterfinal or semi-final. So your winning ratio is some 80% or 90%. Other thing is, they say I need all wins. Literally, you do not have any chance to lose any match. That means you have to be perfect in bowling, batting, strategy. Everything should be perfect, right? The same thing is here. Once even the 6G is saying 99.59 of reliability or even more, that is hyper reliable communication we are talking. I mean, it literally leaves no scope for any error or any miscommunication. Second thing, so that's how we need to redesign or relook the optimum performance of every layer, every element of the network, every protocol, every aspect. It has to be perfect. Then only 99.39 of reliability can be achieved. Other thing is this massive machine type communication. I hope every one of us keep reading newspaper and we keep on hearing that number of wireless users are increasing to lakhs day by day, and the graph is increasing like anything. And whenever there is a load on the system, it is highly likely that it will collapse if not properly designed. And a very interesting thing is, whatever, so what should I say? I mean, it's a beauty of this world or this technology education or this scenario, that whatever we study in the technical domain has a very good reflection in the real world also, or whatever is present in the real world, eventually we are modeling in the technical domain the same thing, right? So there is a very good analogy, be it a CSMA CA network, those who are from with a little bit computer background, whether it's a CSMA CA network, which has a good analogy in a class when every students look, if some other buddy is not asking, then I should ask a question, which is nothing but a channel sensing, or it is multi-hop communication. So we often say to our friend, please convey my message to other. This is nothing but a sort of multi-hop communication, right? This recent incident what happened here in Delhi. See, I think 10, 15 years ago, nobody was really, I mean, there were no such cases of leak and inefficient utilization of government machinery in terms of examination, in terms of performance. But suddenly, why such cases are coming? Because you see the number of students who are appearing in either GATE or NEET or IIT JEE. So now it's really the need of hour that you should look at the way you conduct those exams. See, earlier 50, 100,000 students were there, paper-based presentation, paper-based examination was okay. Even in the recent CBSE, if you know, right? Earlier, the number was not so large, so the manual checking was okay. But now that is not possible. You have to go for some kind of optical checking. I mean, that I think OCR we say, right? But that has to be perfect. Otherwise, you see lots of complaints were there related. So when we say similarly, like when the load increases, the performance of system will degrade. You need to relook to the design, protocol, or if required, a needful change in that. So when this massive machine type communication came into picture, massive machine type means thousands or 50,000 lakhs of devices, lakhs of sensor networks are actually. So when you talk, one example of this is, say, smart building. In a smart building, there are lots of sensors installed. They are monitoring certain aspect, be it a health of the building, be it the ongoing persons, just the counting the numbers, or the temperature variation. Those sensors are collecting those data, sending to some central access point. It is sending to some control center, and it is doing the needful, right? But then if you think, I mean, if there are thousands of sensors, then probably the earlier version of protocols that we were using may not be sufficient. Why? Because I'm talking particularly in terms of multiple access technology. The few of the existing technologies you were aware is for example, you may recall TDMA, FDMA. These are time division multiple access, frequency division multiple access. There you divide time to different users to send the data. When there are 5 or 10 users, it's fine. But you think when there are hundreds of users, that means every user need to wait for its slot, because it's a time slot based, right? For example, there is just one room and the one Atal FDP is going to happen, it's fine. But what if there are multiple FDPs are going on? Can you really ask someone to wait once, let this finish, and then we will go for the second FDP? No, it will take a lot of time. So what's the better way? You have multiple access technology, that is in different way you have given different rooms to them. That is also a kind of multiple access technology, is nothing but. So so those TDM and FDMAs, and especially given the scarcity of the spectrum, it is not feasible to give every user a particular dedicated spectrum. That's how the existing TDM and FDMAs are not capable to serve the strict requirement of this 5G, right? Which talks about thousands of devices. So that's how this motivates us to relook at the existing technologies and to go for some new advancement. That's how this talk particularly includes some discussion on some of the potential candidates for 5G beyond, and upcoming 6G. My particular focus will be on one very recent proposal for 6G, which is RSMA, which is rate splitting multiple access. Though we will have very brief overview of other related technologies also, because RSMA is a more general version. So some of the existing technologies we will relook, so that you get a better idea what exactly RSMA is. So I hope now we have made clear why these new discussions are required. These are just some application and use case scenarios of EMBB, URLLC, and massive machine type communication. This all what IoT, smart cities we have discussed. Yeah, and yeah, very good example of URLLC is this autonomous vehicle and remote surgery. You can imagine a vehicle. Nowadays expressways are there and vehicles are running at 120, 150 kmph. Now, if some malfunction happens or some object is in front of the vehicle or on the road, the vehicle, if it is autonomous, or the driver has very less response time. Few I think years ago, but not so. I mean, maybe last year or last to last year, there was a news there was a famous this Tata group who was the owner who we lost him in one of the Mistri. Yeah, Mistri. I mean, the car was running at some very high speed, and suddenly some obstacle came, and driver was not able to, respond properly. So the response time is very less. Now, this is where comes the picture of low latency communication. You have very less time. I mean, fine, we are moving, and if some object is there, I have seconds of buffer time to act upon, or if on vehicle at 60-70, we have enough time, right? Or the remote surgery where operation is going on remotely with the help of some robot or maybe a person, but those robotic arms are there to help. Some actually expert is sitting at some other place, and then some body is open actually, right? And then there is very less scope of unreliable communication. That is, I actually said yes, go ahead, but because of some error in the communication link, the message was not properly decoded, and rather than 10 ml of required injection, I gave something else. There is literally no scope of error there, right? That actually shows how ultra reliable communication is important in either remote surgery or the autonomous vehicles, right? Yeah, so these are just some visuals of those use case scenarios. Other application use cases are the industry 4.0, where massive sensor deployment, robotic coordination. So these robotic coordinations, also one example is, these Amazon warehouses where, I mean, it's not a small shop where you can go and take the stuff out and deliver. Those warehouses are very large. I mean, Amazon is serving crores of people. So they are multi-floors, multi-sections. So that is not possible with humans. So obviously they take help of robots for that. And then cloud gaming, ultra definition, immersive VR. So there are different use cases for that. Yeah, definitely use case may be different. The motivation to use the 4G or 5G may be different for everyone. It's not same for all. Then, yeah, this is what we were just talking that, the kind of devices increasing. So now you can probably the protocol what we are designing may not be compatible or may not be enough to serve the generation in next maybe 2-3 years. Just after 2-3 years, we need to redesign those things, right? Because the pace at which things are increasing is enormous. Then these are some of the multiple access technologies advantages that it gives you: efficient spectrum uses, simultaneous user access. Simultaneous user access, this is what I said. Now users need not to wait, they can simultaneously transmit, so it avoids the time delay, right? And obviously, since they are transmitting on the same frequency band, so the spectrum usage are very good. That is what is required as of now. So well, this makes the introduction necessary introduction. This is what just the summary. What I said, since 5G was claimed to support massive user density, that's how massive machine type communication came into picture, and that's how there is a need to redesign all those protocols, because those were not designed to serve lot of. See, you can easily recall the time when 3G came or the 4G came. How many people had the mobile phones? Very few, right? But now you see everyone has 2 or 3 mobiles even. So the numbers are increasing at a very large pace. And then intelligent transportation systems are coming, where expressways are coming, where these URLLC communication is required, industrial automations, and also this all makes the this research necessary. Now let's come to the technical part. What we are discussing is multiple access technology. This is a very general mat tree. There are lots of multiple access technologies. We will primarily be focusing on NOMA and RSMA. There are other, they cater different application areas in different scenarios. This is the broad classification of existing technologies, where mostly this orthogonal was being used in primarily till 4G, 3G and 4G, the TDMA, which we have discussed, FDMA and CDMA, but those were orthogonal. They were more from performance point of view rather than simultaneous access, because number of users were very less. So if maybe you can recall that there was a time when we used to do, bachelor's or masters, there was hardly 1 or 2 seminar rooms were there. So because there was no number of events, now there are so many departments, so many centers, everyone is conducting some certain event, and you need multiple such classrooms to perform to conduct these FDPs. So then when this 5G came, then the primary requirement of this 5G was massive machine type communication, and that's how researchers proposed this non-orthogonal communication, which says that you need not to, and the primary factor to make this non-orthogonal communication working was the invention of SIC, which is successive interference cancellation. Will come to that. That allows, because otherwise what happened till now, what communication says in typical words, that you receive some signal, you decode it, and those who have gone through any course on computer networks, we often say in Aloha or in slotted Aloha or in CSMA, whenever there is another user communicating in the same time slot or sending in the same contention window, the collision will happen, right? But now what SIC says, even if there is another parallel user present, but as far as your SINR, not the SNR, but the SINR, which is signal to interference plus noise ratio, is above a threshold, you can decode the signal, decode, subtract from the overall received signal, and then decode the another one. That is what successive interference cancellation. You decode signal, remove the interference, decode next one. That's what the SIC changed. So SIC actually changed the whole game, and that brought these NOMA, SDMA, and RSMA into picture, because all these are mostly based on SIC. There are other methods also to decode. So there is a parallel joint multi-user decoding also, parallel decoding, ML based decoding. Those are there. So broadly, we will be discussing this NOMA and RSMA mainly. So there is a table, small, yeah. So this briefly summarize the pros and cons of these two, OMA and NOMA. And see, having said that, we need to relook at the protocols. We need to redesign those things, because existing things are not serving. That doesn't mean existing things are useless. There is always a scenario where it will work, right? It just, since everyone is in a different scenario, so those things are not working. Otherwise, still there are people who still use those keypad phones. Their need is different, right? Maybe he need a longer battery life. That's how he's happy with that. So when I say OMA, I mean this orthogonal multiple access. When I say NOMA and RSMA, it is non-orthogonal. So when I say resource separation, that means, so resource separation, resource in case of TDMA is a time. It is separated across users. Or in frequency, it is, in FDMA, it is frequency. In CDMA, it is port. When I say NOMA or RSMA, there is no sharing. Every user is transmitting on the same time slot, on the same frequency. That is, the resource block is common. That's how there is no sharing. Interference is minimum in OMA, because since two users are isolated in terms of time, they are not affecting each other as far as there is a guard band in between. If they are transmitting on a different frequency, they are not interfering with each other because there is a guard band. If it's a OFDM or OFDMA, since the resource blocks are different, they are not interfering with each other. But interference in NOMA is there, and we handle it using SIC, as I said, that is managed by decoding. That was the key factor. Spectral efficiency. Now, since spectrum is limited, the primary need is to utilize it as high as possible. So what I feel nowadays, systems are moving towards more complexity, but more efficient in terms of resource utilization. You see, you compare, you see the nowadays the phones earlier, or the new hybrid cars. Earlier, those simple cars, you can get it repaired at any shop in the market. But now these turbo engines, probably they will go to the official company center only, and then they only can handle. But not everyone can handle, because systems are very complex. Expert is needed to handle that, right? So spectral efficiency is definitely, NOMA is not so high, but in NOMA it is very high. Complexity, as I said, in NOMA or RSMA, that is the 5G 6G system, it is very high. So that is just a rough comparison of that. Well, so keeping time in view, probably this TDMA, FDMA, we all are aware there are few drawbacks of TDMA. In certain scenarios, obviously, different time slots are given to the users. In FDMA, we'll quickly skip this, and in FDMA we assign different frequencies. So spectral waste is there in terms of guard band, hardware complexity in terms of sharp filters, and LNA design, and oscillator design, and also similarly in CDMA, maybe some of you are aware, when the number of users are large, codes do not remain orthogonal, they become semi-orthogonal, and that's how the interference problem occur in CDMA. So again, CDMA is not very efficient in terms of serving large number of users. Now, so this is just one animation I got, and credit goes to some Mr. Nitin Gupta. Actually, I got it from LinkedIn, and I got it very interesting running animation, which gives you the idea how the FDD or FDMA or TDD or TDMA actually works, how different time slots are being assigned to users in TDMA and FDMA. Now we come to the main topic. So as the title says, from ARQ to intelligent retransmissions. ARQ was the earlier automatic repeat request method, where whenever there is a failure, you send a negative acknowledgement to the base station or the transmitter that you send again, right? It's something you order something on Amazon and the product is damaged. You just ask Amazon to replace this. That is what the negative feedback you gave, and the system is replaced. But then it takes a lot of time, right? So that's how the HARQ came into picture, which is hybrid ARQ, which is mostly proposed for these upcoming 5Gs and 6Gs, which utilizes certain aspects. We'll see there are actually 3 types of HARQ. Mostly the level 1 HARQ. So HARQ 1 and HARQ 2 are actually what I'm saying is 2 and 3. The normal HARQ was a simple HARQ, which was so where whenever there is a failure, the new packet will be retransmitted, and that's how you decode. HARQ 1 says whenever you receive a packet and if you are not able to decode, don't discard it. Keep it in buffer. Ask the base station to send another copy, the same similar copy, and you try to combine these 2 copies using any combination methods. Say, for example, selection combining or equal gain combining or maximal ratio combining. So in that way, it is highly likely that as compared to 1 copy, you will be able to decode the message in the presence of 2 copies. One from the previous time slot, other is what was just being retransmitted. That is what actually called CC, which is chase combining. And HARQ 2 is based on another variant of HARQ, which is incremental redundancy, which we say as IR combining, where rather than sending the complete packet, you actually just send certain parity bits, right? So those algorithms, both transmitter and receiver are well aware. Utilizing those parity bits, receiver will try to decode the packet. So it avoids transmission of bigger packet. It just perform based on the few transmission of parity bits only, right? So that is efficient in that way. That's how the HARQ 1 and 2. These are just some examples of network in 5G. Presently, HARQ 1 and HARQ 2 is being used because of those requirements. 802.11, the latest Wi-Fi 6, the Bluetooth, low energy, the HARQ 1 is being used. So these are just a few application scenarios. So we start with the non-orthogonal communication. Before going to the retransmission, which was the main motive to discuss, I'll just briefly tell you what is NOMA so that you got an idea, and then you can relate why the retransmission is required or efficient retransmission is required in this case. So earlier, as I said, let's say there are 2 users and both users need to transmit the data. So if you go with the TDMA or FDMA, you need to give 2 different time slots. That will lead to the latency because other user need to wait. What NOMA says, you need not to wait for time slot. You give the same time slot, but given the fact that we have some tool like SIC in mind, as far as those 2 users are differing in power, you can decode them. So what base station will do, so that base station need to transmit some signal to the 2 users, UE1 and UE2. It will assign different powers to those users on the same frequency. So the bigger pink rectangle shows higher power and the green one shows low power. So when these signals, and so it's like x1 plus x2, I'll show you the maths also related to that. When those x1 plus x2 will be received at the receiver, the near user will perform SIC. What it will do, it will first decode the high power signal, will subtract it, and then it will go to decode its own signal. So one SIC need to be performed. The far user will directly decode the signal depending on the SINR. That's what the NOMA is. So you see, within one time slot, the receiver, both the receivers need to decode the signal. Otherwise, in TDMA, in first time slot, user 1 will get, in second time slot, user 2 will get, right? So that's the beauty of NOMA, that it reduces the latency. But obviously, your receiver is more complex because it need to implement SIC, which is successive interference cancellation. So this is what I said, it uses successive interference cancellation at the receiver to separate user signals. And users are assigned different power levels based on their channel conditions. Far user will get high power, near user will get low power. This all we discussed. Just a practical fact, in the 3GPP, if you are aware, this third generation partnership project, which actually handles the ongoing research of 5G and 6G, they are actually performing some experimentation on NOMA. So these NOMA and RSMA, NOMA is still relatively, older version, but RSMA is a very latest one. So it's, in fact, there is no standardization also as of now for NOMA and RSMA. In industry also, RSMA is at all not at all there, because still hardware is being planned for that. For NOMA, there were few implementations, but maybe the NOMA is also not able to support large number of users. That's how researchers started looking for some alternative in terms of RSMA. Used in trials for 5G new radio release 16 in terms of multi-user superposition transmission. These are just some ongoing work related to NOMA. Then, so this is just math. This will give you a feel how the signal is being transmitted. As I said, X1 and X2 was the original signal. P1 and P2, two different powers. Those were assigned to the users. You superimpose them and you just transmit. And then at the receiver, receiver need to perform the SIC. So you see, those who are aware with the physical layer modeling of any communication system, whenever you transmit, the H is that channel representation, which will get multiplied by the signal. N is the noise, which we often model as AWGN, which is additive white Gaussian noise. Often during interview, we ask this question: why additive, why white, why Gaussian, why noise? Very favorite question of interviewers. So you will have an exam also at the end, right? But I hope there is no chance of paper leak. So you make sure that you note each and every aspect of that. So these things may come in the exam. So these are the typical SINRs. So as I said, user 1, which is the weak user, will decode the signal, and then it will perform SIC. And then since the interference part is being removed, second user will only see the SNR, that is its own signal, and the noise. These are some maths related to that. Having said that, or saying that we are working on RSMA doesn't mean NOMA is bad. It has its own advantages. You see, it has relatively better spectral efficiency as compared to NOMA. Fairness is better. At least support better connectivity or massive connectivity as compared to 3G or 4G systems. And obviously, it's a low latency communication. As I said, user sense need not to wait for time slots. So, but at the same time, some constraints that forced us to look for some alternatives. That is receiver complexity. As I said, now the receiver is no more simple. It need to implement the SIC. When I say SIC, so what I'm saying, I will decode the first signal. I'll subtract from the overall received signal, and then I'll decode the second one. That means any error in the first decoding stage will lead to the error in the second. That is very. So when I give a practical real life example, it is more philosophical example. Please try to see those examples as a philosophical examples rather than mapping it point to point, right? It's a broad example of what technical we are discussing here. So this error propagation example is, see, during your bachelor's or master's, whatever CGPA whatever mistake you do in the first or second year, which gets reflected in your CGPA will eventually affect your final your degree grade point, right? So error gets propagated. That's how it will not leave the system. It will get added, and finally it will reflect in your final degree grade point. The same happens in SIC. Whatever you decode at the first stage and perform subtraction, if the signal is not perfectly decoded, it will get reflected into that residual error terms, right? And it eventually spoils the second user also. And then power allocation trade-off, those are more technical in the sense, depending on your channel strength, base station will actually try to assign different powers. So those are very crucial design aspects. Now, in deployment challenge, vehicular networks or dense setup, fast mobility degrades CSI. So this NOMA heavily depends on CSI quality estimation, which is channel state information. That is what base station is transmitting to the user. In between, what is the channel strength, what is the amplitude, what is the phase, that need to be properly estimated. Otherwise, the performance will not be good, which is, CSI is nothing but sort of preparation, right? Whatever task you are going to perform, you should have beforehand, you should know the whereabouts of the task. See, maybe it is related to this event. You need to plan properly that how many attendees may come. Accordingly, you need to select the venue, right? If it is a small venue, then it may be overcrowded. If it is large venue, it may look like empty, right? So CSI is similar. Before transmission, you try to see what is the eventual mapping of the multipath, because when the signal will be transmitted, it will get reflected through the different reflectors and it will receive to the receiver. That will decide the quality of the decoding. So because during mobility, channel changes very fast and CSI estimation is different, that's how NOMA performance in high mobility scenario is not up to the mark. That means when I'm saying on expressways you are going at 150 kmph, probably NOMA is not the perfect candidate. So that's how we need to look for some alternative. Now, the uplink NOMA, at the same time, what we just discussed was the downlink NOMA, where base station is sending some data to the users. Like the way currently I am speaking, I'm the base station, you are the receiver. This is downlink communication. This next is uplink, where users will transmit something to the base station. So at the end, I may ask you to ask some questions also. That will be the uplink communication. In uplink communication, what happens? Again, see, SIC will play a major role here also. Different users, base station will, during the channel estimation phase or the connection phase, base station will tell how much power you need to use, and they eventually will transmit at the same time. And see, interestingly, what I'm discussing is a pure theoretical assumption. I'll show you some of the hardware images also, where some hardware aspects we will discuss. So each user will transmit depending on the channel strength. Now you see that chain: decode U1 signal, perform SIC, decode U2 signal, perform SIC, and similarly, if there are n users, you need to perform n level of SICs. So yeah, in the power domain, this is. So this is typical received signal in uplink NOMA. Okay. Now we come to the retransmission challenge. Retransmission is, so most of us, when calculates the BER or the outage performance, we just say that we have transmitted signal, how much is the BER. Rarely people talks about the retransmission phase, that what if data fails, how you need to retransmit, right? Because we are at the edge of 99.999% reliability, there is a very less scope to do even the errors in the retransmission also, right? But rarely people talks about. It is similar to everyone is talking NEET exam, people are attending that, but rarely people talks about those who are reappearing again. I used to remember, now JEE has a limit, I think up to 2 attempts, right? If I'm not wrong, only 2 times you can. There was a time when we used to appear, there were unlimited attempts. So there was a particular repeater batch where people are preparing for 4 years, 5 years, and they keep on attempting. Nobody talks about their mental health. Nobody talks about whether really he should try for JEE. There are other better options also, depending on his preparation, his background, his economical state, his knowledge. There may be alternatives he can try, but rarely people talk about. There is a blind follow-up that everyone need to either go for medical. That is that time. What was that medical exam? No, that was for PMT. That either you go for PMT or you have to go for this either AIEEE or IITJ. Rarely people talks about whether you should really attempt 5 times. A precious time duration of your life you are actually wasting unnecessarily. Otherwise, there are lots of ways to get success. The retransmission is exactly same. When you transmit once, then how many retransmissions are required? How we can optimize those retransmissions? How they contribute to the overall system reliability, which we are expecting at 99.99%. This is exactly where retransmission comes into picture. So now through this animation, I'll try to show you the existing ARQ, which is nothing but automatic repeat request. And then I'll show you the same animation in terms of HARK, which says how you can combine copies to get maximum out of it. And this is in terms of one user to get you better understanding. So let's say there is one transmitter and it is sending data to the one receiver. Packet 1 it is sending, and the receiver is decoding, and let's say it is successful. So it will send some acknowledgement, which is ACK, to the transmitter. Once ACK is received, transmitter will understand that my packet 1 is successful, and it will send packet 2. Now these cross bars are actually representing packets with error. That means packet 2 is not successful, right? So what receiver will do? It will send a NAC, and receiver will transmit another copy of that packet, that is 2.1. It will be received by the receiver. But let's say that is also failed because of channel condition, or because of some hardware failure, because of oscillator drift, because of LNA oversaturation, or whatever reason, and your packet 2 is also lost. It will again send a NAC to the receiver, and receiver will understand that my 2.1 copy is also lost. I need to send another version of that, and that's how retransmission will happen. In earlier networks, these retransmissions are often limited to 14 to 15 attempts. But now you can imagine where we are talking about high latency, low latency communication, 16 retransmission will lead to a lot of delay. That's how in 4G, not 4G, in 5G and 6G, they have limit the retransmission attempts to 2 only, so that delay is not accumulating. And very interesting thing which is introduced in the 5G and 6G also, age of information. That is how old information is. Where your vehicle is moving at 150 kmph, do you think that 3-second old information is necessary for the vehicle? That scenario is gone. You are somewhere 2-3 kilometers ahead. So, but if you are moving like this, fine. Even the immediate 1 or 2-second old information is necessary for you. But in high speed scenario, the age of information is very important. That age should not be very high of that information, so that user gets the latest update, right? So, so that is the typical standard decoding with ARQ. Now I just rerun the same scenario with the HARK, that is hybrid ARQ. Now, so that you can easily compare the two scenarios, what is the difference? Transmitter sends packet 1 to the receiver. It is successfully decoded. It sends ACK. The packet 2 will come. It is failed now. But now, you see, earlier there was no buffer. But now, receiver will save that copy into the buffer. It will not discard. It will send a NAC to the transmitter. Transmitter will send same copy of that packet to the receiver. Receiver will try to combine the packet 2, which was received in the earlier transmission, and 2.1. It will combine both the copies, and then it will try to decode the information. Let's say even if it is unsuccessful, then it will send another NAC, and transmitter will send another copy of the signal. And now, in earlier ARQ, if you remember, receiver every time was trying to decode the signal with the copy 2 or 2.1 or 2.2. Here, HARK is utilizing 2 and 2.1, utilizing 2, 2.1 and 2.2. So probabilistically, it increases the chance of successful decoding, because you have better information. See, earlier packet 2 also consists of some information, fine, because of the channel or because of the noise or hardware failure, you were not able to decode. It's something like this, say, you are attending lecture of some professor, and fine, you didn't get the things very well in a very well defined manner, but when you discuss the same topic with another friend or attend any other similar session, then you can relate it with the earlier session. Oh, that day professor told this thing, and now what he is telling, that's how the both things are combined, as compared to
they are able to correct it automatically by itself. But at the same time, the delay is also there with buffering, comparing. So latency is also there.
I agree, but see, buffering will not lead to any delay because buffering is happening in parallel to the retransmission. Comparing, I mean, combining. See, yeah, but combining, so it's a comparison. Combining is happening at the receiver, where if you have efficient systems, it will be in nanosecond or millisecond, as compared to the transmission delay. Because if you need to wait for another fresh copy, that means if your transmitter base station is whatever 500 meter or 1 kilometer, that transmitter need to happen. I mean, the transmission need to happen. The transmission delay is quite large as compared to this combining delay. Otherwise, sir, see, nothing comes free. So this a little bit delay will always be there, but it's a comparative delay. You can, by introducing a nanosecond delay, you can avoid that millisecond delay. So it's like that. So so it increases the probability of. So for example, let's say if you are successful at the third stage, that is after combining 2 and 2.1, you are able to decode, then probably you need not to go for the third retransmission. So it saves lot of bandwidth, lot of transmission power, lot of delay. That's what 5G or 6G wants, right? That's how hard. Definitely, you need to, because memory requirement, because you need to buffer the copy. So it's something like this. See, what I believe, complexity is not a bottleneck as far as the kind of pace at which VLSI is increasing. There was a time when we had a VGA mobile camera in our mobile. Now you see 50 megapixel and 100 megapixels within that chip. So VLSI is running like anything, right? So, and investing, you can invest money, but you can't create a spectrum that is naturally limited. So by investing in money, by increasing the complexity, somehow you are trying to compensate that scarcity of resource in terms of time, frequency, bandwidth, and like that. So that's the, yeah. So that is, now here, how retransmission is coming into picture. In NOMA, as I said, what the earlier systems were based upon, they were based upon stop and wait. That is, even in NOMA, let's say multiple users are transmitting. Whenever a packet of one user is failed and it gets the NAC, other users will wait till this packet is being successful after multiple retransmissions. These users will wait, and it is, wastage of their resources, and it increases or adds up into the delay also. So then a very recent proposal came into this retransmission in NOMA, that when multiple users can transmit during first transmission, why can't we allow them to transmit during retransmission also? Because eventually you can perform SIC during retransmission also. So you see what this proposal says, that I'll just briefly show you what is the scenario. Let's say there were 3 users. So this is packet 1, packet 2, packet 3 from different users. And what is the success scenario at the receiver? You see NAC, ACK, NAC. That is, packet 1 is unsuccessful, packet 2 is successful, and packet 3 is unsuccessful. So what receiver will send? It will send NAC, ACK, NAC. Now what will be happening? Earlier, only that user was retransmitting whose packet is failed. But now here we are allowing simultaneous users for retransmission. That is, since packet 1 is successful, so user 1 will send a fresh packet. That means he need not to wait of the success of other failure friends. Packet 1 and 3, since they were failed, the packets will be retransmitted by user 1 and user 3. And this all is happening simultaneously. So you need not to add delay in terms of time. That's what the beauty of simultaneous retransmission, right? And then say just a hypothetical scenario, let's say again your scenario is ACK, NAC and ACK, that is this one is successful now, the packet 2 is lost now, and packet 3 is also successful. So next what will happen, since user 1 packet is successful, it will send a fresh packet. See, this is how the coding is. The complete filled blocks are fresh and these dashed are the retransmissions. So it will retransmit, it will send a retransmission as a dash, it will send a fresh copy. Again, let's say if all these are successful, which is being shown by ACK, then all the 3 will send a fresh packet. So otherwise you think there are 3 users, packet 1 and 3 are lost. Then first user 1 will transmit, 2 and 3 will wait. Then once after successful, user 3 will transmit. Once it is successful, then only NOMA stage will come. So this SIC and NOMA can be modified to allow users participate simultaneously during retransmission mode also. That is what the retransmission in NOMA. Then the topic of this hour, which is the RSMA. RSMA actually takes a different approach altogether to satisfy different needs. As of now, at whatever layer you are, whether you work at physical layer or data link or MAC layer, the typical approach is you have a packet, you have information, convert it into packet, adds headers when you go from top layer to bottom layer, and send the packet in one shot. That's how the till 4G or most of the 5G systems are also based. But when the number of users are increasing, the primary bottleneck in 5G we are facing, and in fact in the implementation of 6G also we are facing, because of the massive machine type communication, because of multi-users, interference is increasing like anything. So when one simultaneously users are transmitting, others users are creating interference to other user, to one user, right? And number of users are increasing, that means its interference is also increasing. Interference is increasing, this means your SINR is decreasing. SINR is decreasing means your decoding probability is getting low and low. RSMA addresses this. It has a very unique approach of handling interference. And probably this is the first time any approach is taking this kind of way to handle interference. RSMA says that rather than sending the packet as a whole, you split the packet, which is nothing but the rate splitting, which is the name says. You split the packet. There is a particular way of combining. I'll show you. You combine in that way, and then user will decode using a particular protocol. And literature shows that this RSMA approach of handling interference is very efficient. It actually dominates over NOMA or UMA TDMA or different scenarios. So this is a very recent proposal in the 6G. Now, this is the typical scenario of view of this RSMA, which shows that. So first you just see how the packet will be prepared, and then we will come to this visual. RSMA is a flexible non-orthogonal multiple communication. See, NOMA is not a name of method, it is a name of approach. You will see NOMA becomes a special case of RSMA. RSMA is also kind of non-orthogonal communication, but rate splitting is added at the top of that. We'll see existing existing NOMA, SDMA, these all becomes special cases of RSMA. So RSMA is a very generalized version of multiple access technology. Core idea is split each user message into a common and private stream. The transmitter encodes and sends a common stream and private streams decoded by respective users after removing the common stream. I'll show you through one animation how is it being happening. The interesting part is maybe some of you are aware about, there is something called broadcast. We often say broadcast this information. Broadcast means information is necessary for all the users. So like that, those AM, FM, those all are under the category of broadcast. Then a special category of that was multicast, where out of the crowd, only a group of users are expected to decode the signal. That is what multicast. Unicast is anyway one-to-one communication. So this common stream, so in NOMA, the signal is broadcasted. After superimposition, you broadcast the signal, and depending on the distance, user will either perform SIC or will decode the signal directly. Here, though the common stream is decoded by all the users. But you see this line, common stream is created for interference management purpose, not because the content of the common stream is intended to multiple users. We'll come to that point. That's where this green beam is not broadcasted, but it is more for the interference management. We'll see how it is. And there is a very typical, and rate constraint is there with the common. Why? Because as I said, the common stream need to be decoded by everyone. That means the rate or the Shannon rate capacity theorem, which you are aware, that is log to 1 plus SNR, need to met in the terms. See, every user, so let's say here, if those are the users, every user has a different channel because some users are near to base station, some users are at the distant. So these users can decode message at high rate because signal quality is very good. SNR is good. So log to 1 plus SNR is also high. But the distant user, because of the distance, because of the path loss, SNR is low. That means log to 1 plus SNR is also low. So they can't decode a high rate information beam. But since I am transmitting simultaneously everyone at the same time, I can't transmit at high rate. Why? Because near users can decode, but far users will not be able to decode. It is something like this, because you all of you are teachers. When you teach in class, you have a mix of janta where some students are very good in grasping the concept. Immediately they will capture, and some are not good, right? They probably either they are not focusing on that or their background is not like that. So you don't deliver very highly technical content. You keep all the janta into mind. So what should be the complexity level of your lecture? You decide basis on everyone, so that the weakest student also get. If weakest will get, obviously the good student will definitely get something out of it, right? Exactly the same concept we are applying here. The rate of the common stream will be decided by the weakest user. The lowest rate which is possible in the network, common stream will be transmitted by that rate, right? So this is a very famous figure which shows that actually RSMA is a bridge between SDMA and NOMA. Researchers have shown that under certain circumstances, RSMA, I also have one figure related to that. RSMA can be treated as SDMA at one side, RSMA can be treated as NOMA. We'll show that. So there is one animation also I have. Yeah, before that, just a very quick maths, how to form the common and private stream. So every user has data. It will split into common and private. Common will be combined like this, WC1, WC2, and form a super common message. And private streams will be encoded separately. I'll show you one animation. And then each user decodes common first, perform SIC, and decodes the private stream, and then combine. How that combination will take place, that animation will make that clear. Yeah, here is the animation. So see, let's say there is a typical downlink scenario where there is one base station transmitter. There are multiple users. So how the transmitter will make that RSMA stream? Let's see. So the general algorithm is for n users. I am showing it for 2 users. So let's say there are 2 users. This base station need to transmit a signal to those 2 users. So what that base station will do? So let's say typical at physical layer, every information is a 1-0 combination, right? After conversion. So let's say you have a data in terms of the user 1 data and user 2, different code rate and rates capacity, everything is given. So first thing, you need to split the data. So what will you do? A message splitter hardware will be there and it will split. Now see, what I'm doing, I'm splitting the data. So the first 2 bits, I'm splitting as a common. For second user also, the initial 2 bits, I'm breaking as a common. And then I will combine. So as I said, WC1, WC2, I will put into one frame, that is concatenation I will perform, and I will make the super common. This is what your super common. And then you will encode channel coding and other error control codings you will perform, and this will have certain additional headers. Now you see, after 0, 1, the remaining bits are 0, 0, 1, 0. So those private streams are being encoded separately. And after encoding, these are the bits. So you see, for k users, eventually you will have k plus 1 streams. Here, if you see, I had earlier 2 users, and finally I have 3 streams, that is k plus 1, right? And then you perform some linear precoding. In precoding domain, we are not going. There are linear precoders like zero beam forming or MRT, but those are we are not discussing. So after combining, performing linear precoder, the signal will be transmitted. This is the story at the transmitter. Now see what is happening at the receiver. That's the end of the story then. What user will do, user will receive the data. First, it will, since common is being transmitted with high power, it will first decode the common data. So if you remember, the user 1's common data was 0, 1, and user 2 common data was 1, 0. The ultimate super common was 0, 1, 1, 0. So it will decode 0, 1, 1, 0. But because this is user 1, and user 1's desired signal is only 0, 1, the first half. 1, 0 belongs to the user 2. So what it will do, it will decode the common data. It will discard the unnecessary bits, will keep the 0, 1, will keep it in buffer. What it will do, next it will perform SIC, it will decode, it will subtract this common from the overall received signal. It will recombine, it will reconstruct the signal. It will subtract, that is, it will perform SIC, and then it will decode that private data. What was the private data for user 1? It was 0, 0, 1, 0. Then I'll combine these two, because ultimate data of user 1 was 0, 1, 0, 0, 1, 0. So after combining these two, my required data for user 1 comes out. The same process will be repeated for user 2. The only difference is user 2 will keep 1, 0 as a common and will decode the second private data. That's the only difference at the user. You see, now this kind of approach was never there for any of the existing decoding methods, where you split the packet, combine and concatenate, and this kind of rate splitting. This is a very unique and recent approach for this proposal for this 6G. These are just some advantages: efficient multi-user interference management and the unified framework for SDMA and NOMA. As I said, I'll show you one figure where under certain power distribution scenarios, RSMA can take the role of SDMA also and can take role of NOMA also. Improves spectral efficiency, robust to under imperfect CSIT, and all these, some of the limitations are there, again, not as standardized. Splitting need to be accurate and beam forming and all. Right, these are some of the theoretical aspects of that. Then, yeah, uplink, where we will discuss the retransmission. So in uplink, though there is no concept of common and private, but user will split the data. So this is what the transmitter block diagram. Let's say again I take an example of 2 users. Out of k users, k minus 1 will split, and kth user will not split. So if I take k is equal to 2, that means one user will split the data, other user will not split the data. And the beauty of splitting, the advantage of splitting is that you have more flexibility in decoding the signals. We'll see what it is. So in splitting block, you see message will be splitted into M1, M2. It will encode it. Power control will be there, and then you superimpose, and then both user will transmit. Receiver side is roughly same. You decode the user 1, perform SIC, decode user 2, perform SIC. This is similar to NOMA. So this is what the signal you will receive. And in terms of maths we can skip as of now. And because there are 3 streams, as I said, the total decoding order is nothing but in which order you are decoding the signal. User 1 or user 2, user 2 or user 1, like that. The decoding order will matter. So because there are different powers are being assigned to stream 1, so S11 and S12 are the 2 splitted streams of user 1. User 2 is sending without splitting, so I'm representing user 2 signal as 2, right? So you see different combinations, permutation combinations are possible, either 1, 1, 2, 1, 2, which is decoding order 1, or 1, 1, 1, 2, 2, or 2, 1, 1, 1, 2. We will just take one example of decoding order, that's it. So these are the SINRs which we have seen in NOMA also. Because when you decode the stream 1, stream 2 and second part of stream of user 1 is creating as interference. So your SINR is H1 by H2 plus H2 square plus noise. That is a typical SINR. You decode and subtract the P11 stream. So you see in the gamma 21, there is no P11 H1 because it is already being subtracted. You already have user 2 and the partial splitted beam of user 1. So that's how your SINR, you decode that and remove, and user 2 is a simple SNR, right? So now the interesting part of the retransmission scenario, how this splitting in RSMA actually contributing to the efficient retransmission scheme. So retransmission simply, I mean, everyone understands when the packet is lost, you need to retransmit that copy. What happens in FDMA, since they are transmitting on the same time slot, on same frequency, on different frequency. So let's say this example shows that this is my time and this is my frequency. So on different frequencies, this frequency is for user 1. Sorry, this is for user 1 and this for user 2. And see, what is written is S1 is decoded, S2 cannot be decoded. That is, at two frequencies, user 1 is decoded while user 2 is not decoded. So it's simple retransmission that user 2 will be retransmitted and user 1 will transmit a fresh packet because it is performing the transmission on a different frequency. So there is no interference at all, right? That's a typical retransmission in FDMA. I'm just giving you an overview of existing transmission so that you can relate how the new one is more efficient in that way. In NOMA, what is happening? Since the signals are superimposed in terms of power at the same time and frequency domain, so let's see, I have transmitted this. And what happened? See, I'm sending NAC and NAC. That is, both the packets are lost. That is, if I'm not able to decode first copy, I cannot perform SIC and I can't decode the second one also. So if I stuck at packet 1, my packet 2 is also stuck, right? So it's something like this. If your CGPA or you have a certain, like in our university, there was a rule that if you have this many Fs in first year or any year, you can't go to the next year. First, you have to clear that. So if you are not able to, decode the signal at the first stage, you can't go to the second stage unless you clear the first one. So if at the SIC stage, if you stuck, your second packet is also under question, right? So NAC means packet 1 is lost, and because packet 1 is lost, packet 2 can't be decoded. So what transmitter will do? It will retransmit packet 1. Packet 1. So now you have two copies of S1. Either you go with the ARQ also, that is, you just try to decode the signal based on the S1 retransmission, or you can apply HARC also, where you can combine the copy of this S1 retransmitted copy and this earlier copy which you had in buffer, which we have seen in the HARC. You can combine these two. If you are able to successfully decode, then you can perform SIC and you can decode the second copy also, which was actually stuck because of SIC. And here in this particular example, we assume that decode and remove it, and then S2 is also decoded. So with one retransmission, even though S2 was failed, you were able to decode. So in a way, you avoided one retransmission at least. But now see the RSMA, where there were three streams, if you see, S11, S2, and S12. And let's say, just in one hypothetical example, I'm assuming that my scenario is NAC, NAC, NAC. That is, at the first SIC level, you stuck. So second and third are also not clear. What will you do? One is just S11. So transmitter need not to transmit the complete S1 packet. It just need to transmit a part of it, right? And once that part, so S11 retransmission, you see. Now, if the receiver is applying HARC, this S11 retransmitted copy will be combined the earlier buffered copy of S11, maybe using CC or IR, and then once it is decoded, you decode and remove it. Then you come to the S2, you decode. So here we assume, let's say if your SNR is sufficient enough, you will be able to decode S2 also, and you will be you go to the S12 and you decode S12 also. In the paper, they have discussed, authors have discussed that, let's say if the SNR of S2 is not reliable enough, or you are not able to perform, you are not able to continue SIC, you can always request the transmitter to send another copy of S2 to perform the combining scheme, right? Right, we are almost at the end of the session. Just another visual which shows that how splitting actually helps. That is, I'll show you scenario where only 1, 1, 1, 2, where two users are splitting into two packets, and one user is not splitting. So if you see, user 1 is splitting in S11, S12, user 2 is splitting in 21 and 22, and user 3 is sending as such. So in the first case, let's say SIC can't continue at the, so you stuck at S2, 1. That is, you are not able to decode 2, 1. What receiver can do, given the channel condition, it can ask user 1 to go for 3 splitting. I'll show you mathematically also with a toy example how this splitting into more numbers actually helps. So once it is split into, user 1 is split into 3 parts, 1, 1, 1, 2, and 1, 3, your SIC can be continued, right? So just by splitting more in more numbers, you actually can, otherwise what will happen in the case 1, receiver will ask transmitter to send another copy of 2.1, that will add into delay, wastage of resources and power, transmission time, and then it will combine, so it will add into delay also, and then it will able to decode. In the second case, if you split into 3 cases, you can continue with the SIC, so you need not to request for a retransmission, right? This is another aspect where authors have shown that actually splitting into multiple numbers will actually help, but there is always an optimization problem that in how many numbers you should actually split. So we'll skip that. Now see one example based on that how splitting into 3 instead of 2 actually helps, or how it avoids retransmission. Now see, so how splitting into 2 versus, okay. So I just take a practical example. Let's say your payload is of 9 bits, and overall resource block, that after adding some header, footer, or controlling bits or channel coding, the total packet that you need to transmit using BPSK is the 12 symbols, right? So these are just typical rates. So some of you are already aware. The way we rate, we define the rate in coding theory, it is typically K by N, and redundancy is obviously 1 by R. So this is case 1 where user 1 was splitting into 2, that is S11 and S12. So since my overall payload was of 9 bit, how I am splitting into 3 and 6. There are multiple combinations available. Just for the example purpose, I am taking this particular case of 3, 6. Otherwise, it may be 5, 4. It may be 7, 2. Right? Many combinations are possible. So now what will happen? Since I need to make the, see, if you remember the animation, the 2 splitted stream will eventually be superimposed. That means their size should be same in order to superimpose. So because the overall size is 12 symbols, I need to add some redundant bits in terms of coding or something to make the overall size as 12, which is this. So 9 plus 3 makes 12, and 6 plus 6 makes also 12. So my ultimate packet size is 12 now. I am ready to superimpose, right? But here, the game changer factor is this: rate and redundancy. Please keep an eye on that. So my rate here is 3 by 12. Why? Because I defined the rate as K by N. So your 3 were the original data bits, and total size is 12. So that's how we define the rate. Original data divided by total bits. So that is 3 by 12, that is 0.25. Redundancy 75%. S12, the data bits were 6, total size is 12. So my rate is half, my redundancy is 50%, right?
That is the number the redundancy rate will increase after
That's the key point that you got. The RSMA, the whole idea of RSMA is based on redundancy. That when I split into large numbers, so my data bit, so in the next example only I'll show, my data bits are 9 only, but I'll show that when you split into more numbers, obviously the bits per packet will decrease, but eventually you need to make the size as 12, so you pump more redundancy. More redundancy means high reliable data, highly likely that you will decode the data. That's the whole key point in RSMA. So let's say, so this is based on that the earlier figure where SIC was stuck when I was splitting into 2. Then once I split it into 3, the SIC continued. So you see why it continued. So again, those 9 bits I am splitting into now 4 plus 2 plus 3, again 9, but 3 packets now. But because the 3 packets need to be superimposed, the packet size should be 12. So now I need to add redundant bits. So now I'm adding redundant bits. 9 plus 3 make 12. 10 to n is also 12, and 4 8 is also 12, right? Packet size are same. I will now can superimpose those bits. Now just look at the rate figure. Now the rate of first is 0.25. I have not changed that intentionally because in that figure, if you remember, my 2,1 was stuck. 1,1 was able to decode. So I need not to play with the 1,1. That rate my channel is supporting. Channel was not able to support 2,1, right? Now, so the rate of S12 I have decreased. It becomes 0.16, and the rate of 13 is now 0.133. Let's look at the redundancy numbers, which is 75, same as the first one. The redundancy of second is 0.84, and this is 0.67. Now, because redundancy of 1, 2, so if we go back to that, just quickly. Here there is line written, decoding S12 with low rate. Now you see what was the rate of S12. It was very low. Now what is happening physically? See, this 2.1 is stuck, not able to decode. Why? It is facing interference from 1.2 and 2.2. What change I have made? Now I am able to decode. Now what I am doing, I am first decoding S12 first. So you see, earlier 50% of the user one's packet was creating interference to second user, that is 2,1. But since I have broken the packet one user into 3, so per packet data bits is reduced. And now you see, if 2 of the frames are decoded, how much data is remaining into third part of the user one? Only 33%. So user 2 is essentially facing a reduced amount of interference, and that forced us to decode the user efficiently. That's the whole beauty of this RSMA. So that is what the numbers in the RSMA actually shows, that since the redundancy has increased, you actually can decode user first, second part 1, 2 efficiently. It reduces the interference for the user 2, and SIC can continue. These are just some visuals that we are currently doing at our lab in IIT Roper. We were implementing these NOMAs, and once we have developed those algorithms, then we tried to see how those are performing in hardware also. So we purchased some end. So the technical discussion is over. This I'm just giving you some visuals of our hardware experimentations. We have purchased software-defined radio, this N200, we made it as a transmitter and other receivers using N200. In gallery, we have performed this. Q-NOMA was just a variant of NOMA where we transmit on orthogonal, on I and Q branches to avoid the interference. So that was one hardware experiment we were doing. And this was another hardware experimentation that we are doing. It was supported by a project under Ministry of Earth Sciences, Deep Ocean Mission, where they try to optimize the performance for underwater communication. So here also I was trying to deploy RSMA into underwater, and I was trying to see whether performance can be improved or not. In underwater, if you are aware, RF doesn't work in RSMA at longer distances because of the conducting water medium. There, mostly for longer distance, we use acoustic communication. So so these are the transducers and receiving transducer. Through that, we were doing acoustic communication. This water tank was filled with water, and then we were doing this communication. So so this actually figure I was talking, which shows that RSMA can actually be thought of, can take different forms of NOMA, SDMA, and multicasting. You see, rate splitting, that is user 1 and user 2, splitting the packet into private and common, and then forming the complete WC, right? If you remove the common stream of user 1 and private stream of user 2, then it is nothing but a NOMA. If you remove the common streams of users, then it is nothing but the SDMA. Though we have not discussed SDMA, but in SDMA, you actually form different beams to particular users to serve separately. So the problem with SDMA is that if there are tens of users, maybe 4x4 or 16x16 antenna can make 16 beams. But when there are 50s of users, making 50 beams actually is very difficult. Beams will start overlap, so they create interference. That's how SDMA may not be efficient for multi-user scenario. Then for OMA, if you remove the common and private, common of one user and common and private of other, it is actually just one signal, which is nothing but OMA. In OMA, only one user transmits. And multicasting is, that is, the data is for all users. That is the common part. You remove private streams, combine only common, and when you transmit, since common will be received by everyone, it is nothing but multicast. So RSMA is so powerful that it takes all existing technologies, that is OMA, multicasting, SDMA, NOMA as a special case, right? So so nowadays, we talk about software defined radios. Your radio is software defined. You just change the protocol software wise and your system will start. Otherwise, earlier, your hardware is tied to either TDMA or FDMA or NOMA. If you wanted to change the protocol, all things need to be changed. Like with our phone, earlier they were compatible with 3G. Once the 4G came, we need to purchase a new phone. Now it is compatible with 4G, but now I need to purchase a new one because it was not compatible for 5G, because these are not software defined radios. Once that software defined radio will come, probably you will purchase just one phone, but that will kill the market of all mobile companies. And you just, OTA will come and it is compatible with 6G because it's just a software defined radio, right? That's what the beauty of software defined radio in terms of when you go for a generalized schemes like RSMA. These are just last slide, which shows the different application scenarios of RSMA in different areas like selfie massive MIMOs, cloud RAN, mmWave, RIS, which is a very hot topic. In fact, yesterday only when I was traveling to Delhi with Vande Bharat, I got this news in newspaper that Jio has recently launched his what was the name? Smart wall. That it is not the typical wall where because of the wall your signal penetration is actually goes down, so you don't get the signal. What they say, they will actually make the walls using this RIS, intelligent reflecting surface. So rather than killing the strength, it will actually empower the strength. So you will have a better strength. Recently, they have shown in some technology event that this RIS based smart walls by 6G Geo. For rate splitting, for RIS, a few people have developed some prototype also, some diode based. This is not my area, but yeah, there are specific material is required for that RIS. Yeah, and non-terrestrial communication, that is satellite communication, wireless federated learning, non-orthogonal unicast, low resolution DAC, AICTE, which is the very latest proposal in the 6G, that you will not only communicate, but you will sense also, which is very crucial for high-speed vehicular scenario, where anyway you are sensing you are anyway communicating to the base station. But if that communication will lead to tell you that there is an obstacle also, you can accordingly manage your driving to avoid any accident. So AICTE is another one very good area. And grant fee, multiple access, massive. So these are some of the application areas where people are trying to deploy RSMA to improve the reliability and network performance in real time. Yeah, that's it. Thank you. So, any question related to your upcoming quiz? Yeah. Yeah, yeah.
The best part was whatever concept
Please.
stated with very nice, daily concept. So that is a good thing. What
See, AI is what this is how I see. Well, first I come to the first point. This real life analogy. you just need to push and things come out. I often say into the class, see whatever I'm teaching, I'll also try to match it with the real life analogies, and you also. And I recall one very interesting incident. I was probably teaching this error control coding, or some communication course where there was a source coding which shows that you need to, the packet size will large if uh, some information is coming, or I don't recall the exact context, where it was something like this, that if the information is known, you need to add less redundant bits or something like this. So after the class, I gave an assignment to students that whatever we discussed today, please write a short note on how is this applicable in the real scenario. In fact, I gave, if I can recall, I gave this question as an exam question in the end set. And one student came up with a very innovative answer. I still recall that, though not with the proper context. So the context was something like this, that when the information is known, your message length is also reduced. I mean, you need not to add extra information to that. That was the technical context of that class lecture. And he gave one example. Sir, when you met with someone and you save his name in the mobile, then if it is a first meeting, then how do you save X, let's say Suresh, let's say I met him in IMC, Suresh IMC, और उसने, and he said, sir, I am working in BITS and I am friend of wise person. So some extra things we always add. Otherwise, if I add only Suresh, I'll probably forget. So I'll add some keywords, Suresh IMC, Sai Raj friend. But when I met every day, I am familiar with you. You need not to probably add those many headers. You just add Suresh IMC and it is enough for you to recall. So, I mean, yeah, that is one philosophical analogy of that technical concept what we were discussing there, that when the message is known to you, you add actually less redundancy or something like that. So people also come up with very innovative way of relating things with the technical aspects of what we discussed. Okay, come to the second point. So what I see, AI is more, or at least the limited knowledge that I have related to AI is more about how you are implementing. See, you should be clear with the motive. For example, I'm clear that I need to reduce the retransmission using this algorithm, right? Or I need to keep a trend, or I need to, so there are traditional way of estimating channels also. Now people have designed AI ML enabled channel estimators, which actually tracks the channel and estimate what channel is going to be, right? So AI is, so whatever I'm discussing, it is more at the protocol level. Once you go to the implementation part, you can always apply AI. Or you can, so let's say I talked about NOMA is very sensitive to channel state information. With the traditional methods of channel estimation, those are not perfect. We always have, so in fact, related to hardware, when we say we superimpose the thing, we recently got one review comment from one of the reviewer, and that forced us to realize that what we were doing was actually an assumption. In reality, it doesn't happen. That in reality, when different signals are being reached at the base station, they are asynchronized. They are not perfectly overlapped. So what SIC you perform, that is actually asynchronous SIC, right? So, and it is very difficult to remove using traditional methods. But these AI ML based channel estimators, these are very perfect. In fact, you see, at least the literature what I have gone through, whatever performance you have seen with the AI, I mean, when you compare the traditional method and the AI based method, obviously the complexity will increase. There may be some additional delay in terms of delay and this training and testing. But once it is trained, it performs like anything. So it is. So for that, your ML need to track the channel or the pattern that given these channel conditions, distance, power and all, how many times I'm being, how the signal is required to be transmitted. Depending on that, it can optimize the parameters. But eventually retransmission need to happen. It can only optimize the thing. Or if I am going for whether RSMA or NOMA, how should I optimize those parameters given this channel condition? What should be the optimum transmit power? What should be the optimum redundancy bits, all those things need to be decided using ML. So that is, I see more as an implementation point of view. It's up to you how do you implement, whether you wanted to make system more complex but performance effective, or you wanted to less complex but, let's say, fine in terms of performance. So these protocols are, available for both ways. Go for AI, then get a better performance, but complex systems, go for a traditional methods. The system will be efficient but less complex. That is more at implementation level.
Based communication.
So,
Well, I'm probably not the correct person to, because I have, again, limited knowledge on that hardware part. Maybe Deepak can tell you better in that. He is in industry.
okay.
Okay.
Thank you. Thank you.
But what I see, at least the kind of, information we get, the way so you take the example of, let's say, mobile, it is not SDN completely. See, SDN is a very wide thing. In a way, if you are able to address any security vulnerability through software update, it is also in some way SDN or software defined radio, software defined networking, right? It may not necessarily be make it compatible to 4G to 5G or 5G to 6G, right? Or sometimes there are many bugs that they address through the OTA only. You get some updates, even in Windows also, you get that update. But yeah, major updates required hardware change. Like if you remember, those who have recently upgraded to Windows 11, many of the platforms running on Windows 10 were not compatible to 11 because there was a processor requirement. So like that was not. But within 11 or within 10, you often get Windows 11 H1, Windows 11 H2, Windows. So those were also upgrades. Those are also some initial level of SDN. So in a way, we are moving towards that. Most of the 5G base stations are now compatible to that SDN. But yeah, SDN is a very wide. Sitting here, we can't see the end of the top of SDN that, oh, if we have implemented that, then we'll say we are top of that. Daily a new era of SDN is coming into picture in terms of network slicing, in terms of this RIS, in terms of efficient routing.
Very innovative field. Daily innovations are going on because it is totally application based. Thank you, sir.
If the system is power efficient,
Yes. See, if you see in a global picture, if I'm able to reduce the number of retransmissions, I'm saving power. But there is a catch. This reduction in transmission is coming at the cost of complexity in the circuitry, right? So when you do the holistic analysis, once you are taking into consideration the reduction in number of retransmission or the energy saving that happened because of the retransmission, you need to take care that power consumption that added because of the system complexity also. But power in the signal processing is always far less than power required for retransmission. So that's how, let's say if I talk in terms of rough bigger numbers, if you save 1 milliwatt of power, then maybe you need to invest some microwatt of power. Still you are in a saving.
or in terms of redundancy, as redundancy increase, power required more.
No, see, my packet size is still 12. Eventually at physical layer, I need to transmit 12 bits. That 12, see, for physical layer, everything is a bit. Whether it is data bit, it is redundancy bit, it is header, it is footer, I don't care. See, for director, everyone is a student. Whether it is civil student or electrical student, he doesn't care. For me as a HOD, I may be caring more about my electrical student. कि भाई ठीक है, resources should be available to them. For CSE student, whenever they come to me to, sir, I need SDR, I say, देखो भाई, there is a scheduling. Obviously, I'll prefer my students. If then time slot remains, you also can borrow. So for director, if somebody says, sir, I need to do something, okay, see, everyone is equal. Okay, you maybe go for a chip-based system or some random slot allocation and it is fair. So for physical layer, everything is data bit. Whether I am adding redundancy bits or those are data bits, eventually he need to put some microwatt power to transmit or transmission of that bit. So at physical layer, it doesn't matter. It is upper layer understanding that if it is redundancy, I have more help in decoding the data because that's how redundancy is. If it is data bit, then there is always a chance of error. That's how the whole coding theory is based. You have low code rate, better reliability, but data rate is also low. You have high code rate. That's the trade-off. See, there is no straightforward answer for this, but it increases in the sense, because I'm going for non-orthogonal communication, I'm allowing all users at the same time. So now if you compare at either TDMA or FDMA, where I need 4 times system utilization, in one utilization, I am serving all the users. So let's say your 30% spectrum utilization has increased, right? But yeah, no. See, eventually I am transmitting 12 bit only. Again, the same answer. Whether it is data bit or redundancy bit, it doesn't matter.
No, but if I add more redundancy bits, that means my message will become longer. So I'll be able to send less.
My packet size was 12 only. I am maintaining, see, your point will be valid when I am increasing the packet size. But there is a catch, which probably you have realized. My data rate is decreasing because data bit is decreased. But see, the catch is nothing comes free in this world. Right. If I am trying to reduce the retransmission, somewhere I need to reduce the data rate. That's how it says that you can decode or you can continue SIC by reducing the code rate. So if you receive some packet with a low code rate, you will be able to continue. So though my code throughput is decreased a bit, but there is a trade-off. That's how there are optimization algorithms that given this minimum data rate, maximum power, how the retransmission can be reduced or whatever optimization problem you need.
Means we can accommodate more and more devices.
Now, this is also very good catch. In theory, when we were designing algorithm, those are designed for K user, number of users you perform K SICs and all. But when we do it using SDR practically, then we observed that, thank you. Please. Then we realized, given the limitations of hardware, there you have imperfect CSI, you have imperfect SIC, you have oscillator drift, you have LNA saturation, you have oscillator drift. All these lead to some error propagation, and we were not able to decode more than 3 or 4 users. So obviously though we have not included all the transmission streams in terms of coding and all, I hope once we include that coding block into that, maybe users can increase, but obviously any system number of users will increase, system will collapse. Whether it's a railway station as compared to airport or the classrooms, right? You can't compare the security at airport similar to the railway station where there are hundreds of users coming like anything.
Capacity is a limit,
very much.
Right?
So that's how 5G came with the concept of small cells. Yes. Rather than having a one cell of large user, you make small users that is easy to accommodate, though at the cost of complexity.
Right.
So
what is the technical prospects between the NOMA and OFDM?
NOMA and OFDM.
Basic differences between the OFDM and NOMA techniques in the technical prospects.
NOMA, OFDM, if you see, that is a kind of a form of
orthogonality.
Why? Because one user gets one resource block. If there are tens of resource blocks assigned to 10 users. So that is a kind of orthogonal communication, but obviously more efficient than other contemporary communication, OMA communication systems like TDM and FDM. In OFDM, you can simultaneously serve multiple users, right? You divide the frequency into different, subcarriers, and then you can. So that is a kind of orthogonal communication only. NOMA, in a way,
it's non-orthogonal.
It's like non-orthogonal in one resource block. So you can consider like there are 4 resource block, and in OFDM, either 4 informations are going or one information of one user is going in one resource block. So in OFDMA, you can serve 4 users. And in each subcarrier, now if you apply NOMA, then in each subcarrier you can apply NOMA. So it's like, so if you are aware, there are practically the systems that are being implemented are TDD OFDMA, TDD OFDM, TDD FDMA,
FDM.
FDD TDMA,
TDM, ठीक.
yeah, or I mean the variants of that.
Variants,
So
yeah.
that's how a variant like NOMA OFDM can come. OFDM, NOMA is just superimposing different users in terms of power at one frequency. That frequency may be one subcarrier of OFDM.
RIS sir system is applicable only for 6G or 5G, yeah, or both. Reconfigurable intelligent surface.
So we
Like
often
this.
ask one. In fact, I used to think it like this: if in 5G I can propose network slicing,
Network slicing.
why can't we apply in 2G? At the time of 2G, you could propose that, or in 3G also you can propose. Why it is being talked about for 5G or 6G only? See, but there are many factors.
We are in current generation, na? Like that.
What is so special in current generation? See,
Enhancing
that
the data
time,
rates.
that generation was also current.
Yeah.
When 3G came, we were happy like anything. 3G aa gaya. We can have those video talks. That was, see, our fathers also have seen the latest trend that time. Now they are outdated.
Sir, we are talking about the
Currently, we are
6G, then
the current
it can
generation.
be embedded with the AI and ML also.
The way you are looking at AI, that time they were looking at FM or AM when it was get introduced.
Yeah.
Right? Our children will see this generation, they are outdated. How do they know? Every generation has this charm that I am the latest one. You just wait for 5 years. Quantum will change everything.
Okay,
This is what we were just discussing. It's gonna change the way we encrypt the things, the way we provide security, the way we communicate. You see the RSMA. It has changed the way we transmit the packet.
Definitely, sir.
Why? Because the requirements are new. The constraints are new. So I often used to see the problem was why we are talking in terms of 5G only, because first thing is earlier there was no such requirement. How many users were there who were actually accessing the communication inside the walls? Earlier we were at landlines. Hardly anyone cares whether signal is inside or not. There was no such requirement, right? No.
Thank you, sir.
So now, but because second thing, we are talking about OFDM. It looks like very recent development. I think most of you are aware, the first paper on FDMA, I mean, who has coined this? The idea of OFDM is I don't recall the exact number, but it is somewhere around maybe 70s or 80s.
Yeah.
Very old.
Very old.
We do research. It is research. The idea of rate splitting first came into picture in 91. The author presented the idea of that you can add a virtual user, but why nobody was talked about that time? Because there was no hardware support. You were not able to implement that OFDM because of the non-availability of hardware to implement FFT or DFT. But now once the VLSI came to that stage where you can deploy that FFT in terms of DFT, now you are applying OFDM. So many of the things people have coined earlier, but because OFDM, because the VLSI was not supporting, we were not able to implement. It is only on paper. Similarly, it's not like that this RIS idea, maybe you just searched on Google, maybe somewhere in some corner of the block, some guide and student will be discussing this. But somehow because they don't have resources, they are not able to implement it. See, many of the researches, I don't know how much true it is, but just because I read somewhere, many of the inventions happened in India way before. But because we don't have that global overview, in foreign, since they had power, they had news, they had media, they were able to channelize it and everyone knows, okay, this invention goes to that need. But actually invention happened somewhere else. So that was also one challenge that earlier many people have coined these terms. But because we were not supported by hardware, and unless thing is implemented, it is not in the reach of people. Only the person in the room or in the lab will be able to know that I have coined something.
ठीक है, sir.
Definitely. Very true.
Thank you.
So often our VLSI friend keep discussing that they have that nanometer length discussion related to, I'm not aware with that. So that's the bottleneck, that how low they can that one, right? So probably by time that hurdle will be removed and we'll have some new more technology. Okay, what is the mode of? Okay, mostly the second part of discussion was based on that paper only. Yeah. So how the discussion will happen? That is also I have shared. No, I have not shared. Oh, I have shared the name only. Though that is available on IEEE, but I'll share the paper also. But just in order to maybe just for paperwork, I can quickly go through the paper maybe after break. So yeah, though, but as I said, the main gist I have already covered in the slide only. So it will be easier for you to, otherwise that's a 14 page. There are lots of other things were already there, but we can quickly go through that also, not an issue. That's how I said, at least for paperwork, we can discuss it. Sure, that will. Great, great, great. Oh, I am comfortable. हो ही जाएगा एक्चुअली हम उसके पहले ही खत्म कर लेंगे maybe I can share the paper on this. अच्छा हाँ अच्छा 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 sure 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 भेज दूं?
ग्रुप पे डाल देता हूँ। अभी मुझे ये चाहिए होगा ना, मुझे टेस्ट भी बनाना है सबका।
तो व्हाई डोंट यू आस्क क्वेश्चंस फ्रॉम एक्सपर्ट्स इटसेल्फ? पांच दो क्वेश्चन सब लोग दे दें, आप उन्हें कंबाइन कर लो।
सर आप लोगों ने दी तो मुझे ही ढूंढना पड़ेंगे
नहीं, हम क्वेश्चन आंसर दोनों देंगे।
ठीक है,
ये पूछा मतलब इफ
नहीं
यू
जनरलाइज बनेगा लास्ट में। मैं कर दो फोन, क्वेश्चन आंसर एक बोल दो बस ऐसे।
तुम्हारा ये वाला है जतिन गौर भारती विद्यापीठ, ठीक है?
हाँ जी।
और किसी को सीसी भी करना है, मैडम को करना है?
नहीं आप मेरे को भेज दो, इस ग्रुप पे ही भेज दो।
ये हटा दें।
जतिन, जतिन आना नहीं है?
एक बार आप आ जाओ जतिन सर।
जतिन सर आ जाओ, we'll have photograph complete.
वहीं पे खड़े हो जाओ सबसे।
बिल्कुल रुको बेटा, सैम सर आओ, तुम लोगों ने भी अटेंड किया लेक्चर, आओ, ऐसे नहीं पीछे हटते, आओ तीनों। हम ऑफिशियल नहीं देंगे, बट आप लोग को होना चाहिए ना बेटा।
नीचे बैठ जाओ, नीचे।
इधर बैठो, उधर
आगे आ जाओ, आगे इधर आ जाओ। आयुष इधर आ।
आयुष को सेल्फी ले ले। Thank you, sir. It was a nice session.
सर ये लगा तो
अच्छा अच्छा।
नहीं पकड़ ला
नहीं ठीक ये, हाँ इधर ही जो गेस्ट हाउस है। चलिए पॉकेट में। हाँ ओके। हेलो, इज इट ऑडिबल? ऑन करना पड़ेगा। ऑन है इधर से? हाँ इधर से।
हेलो सर, आ रही है पीछे से, वॉइस बढ़ा।
तो बताइएगा जब मैं बोलूँगा, सो दैट वी कैन ट्यून। हाँ हाँ, क्योंकि ऑलरेडी डिस्कस्ड ही है वो तो। हाँ आए दीपक, कैसे हाल चाल? कल पता कल पता चला दीपक बाबू आ रहे हैं, हमने कहा चलो फिर बढ़ते ही चलो। अभी यहाँ कहीं दिल्ली से ही आ रहे हैं? कहाँ से आ रहे हैं? चंडीगढ़ से। अच्छा अच्छा। नहीं नहीं, हम लोगों का एक्चुअली कुछ और प्लान है यार। हाँ प्लान चेंज हो गया। हाँ उसका कुछ कुछ आ गया। अश्विनी बोले तुम इधर ही हो तो फिर हम लोग के साथ ज्वाइनिंग कर लो। चलो। अच्छा तुम एक दिन वो आपके भाई मिले थे, वो क्या नाम है? नितिन। हाँ हाँ, वो बता रहे थे कि यू शिफ्टेड टू चंडीगढ़। अब क्या करें, तुम्हारे अपडेट तो आते नहीं। शादी के पहले तुम कम से कम कुछ अपडेट करते थे, तो तुम गायब ही हो गए बिल्कुल। कोई नई बात नहीं, शादी के बाद सबका ऐसा ही होता है, कोई नई बात नहीं। वो हमें ऐसा लगता है कि हमने सब लेटेस्ट टेक्नोलॉजी बना ली है, समय के साथ वो कब आउटडेटेड हो जाती है पता नहीं चलता है। हम यही सोचते हैं बस ये काम हो जाए, बस तब से हम फ्री हैं। जरूरत क्या है पढ़ने की? सबको यही लगता है, अपना काम देख के लगता है तो ये किया क्या था हमने 5 साल में, यही किया है क्या? सबको ऐसे ही लगता है। नहीं अभी करंट, जब मेरे ख्याल से लास्ट टाइम मेरे को जो अपडेट था वो यू आर इन दिस पेटेंट रिलेटेड फील्ड, अभी उसी में कंटिन्यू कर रहे हैं। कंपनी चेंज की है। हाँ बट प्रोफाइल वही है, तो उसमें भी पेपर लिखने की क्या रिक्वायरमेंट है? खैर वो बना रहे तो अच्छा है, बना रहे तो अच्छा है, बट कितना टाइम मिल पाता है? अगर ऐसा है तो बढ़िया। तो खैर बढ़िया। अच्छा अच्छा। हाँ शुरू करेंगे। हाँ ओके 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 श्योर। Welcome again in this paper discussion session. Though the gist of the paper I have already covered in that uplink RSMA retransmission concept that we discussed in the slides. But just to give more broader picture, the content I have taken from this paper only. And this author, this Bruno Clerks, this is actually, he is the key person who coined this term, rate splitting multiple access. He himself is the author of this. So I have highlighted certain things that may be good for you to also read through. So that will give you a complete picture why that's what we have started, this multiple access schemes are already there, but then why there is a need to devise new, why there is a need to think new mats. So this line actually justifies that these methods are not suitable for applications involving massive low power devices connected to a common base station. So whenever there is a massive connectivity required, which I said is a key requirement for 5G also, which talks about massive machine type communication. So in fact, not related to this paper, but since the context of massive machine type communication came into picture, there is a recent proposal in multiple access technology, particularly tailored for massive low power devices. This is called URA. It is unsourced random access that is particularly tailored for large number of low power devices, where you need not to send the node ID, because what they feel in these kind of massive deployment, the content is more important rather than who has sent it, right? If there are thousands of sensors, you really don't care who sensor has sent this information, but the information is that there is a temperature going up or there is some system failure, right? So from that perspective, a recent proposal of URA also came into picture. Then now see, so just to simplify the things, when we say that we can split, so this line actually says what I was saying. Uplink RSMA is studied in this and was first proposed in this 19th paper is that the one I was talking somewhere around 90s paper, which theoretically coined the idea of splitting the users. And they say that since single user is splitting the data into two, this can be considered as adding a virtual user. Once you split the data, you think there are two users and then they are actually communicating, right? And then you transmit a superposition of these two streams. Then, because the paper is in detail, they have shown that, and as I said, under specific circumstances, the RSMA can take form of NOMA, can take of SDMA. So they also show under certain circumstances, NOMA with time sharing can achieve the same capacity reason what RSMA does, but it needs multiple time slots, right? RSMA can do it within one time slot. Now, this also talks about the type of HARC that we discussed, that in paper, what they are saying as type 1 HARC, which is a simple retransmission, that when you transmit a packet, it is failed. You send a NAC and transmitter will send a fresh copy and you decode with that second copy only, right? HARC says that you combine the previous failed copy and the new retransmitted copy, which is actually the HARC 1, which is CC, which is chase combining. And the third one, this third type of HARC, which is incremental redundancy, there rather than sending the complete copy, you just send some certain parity bits, right? HARC with IR, which is incremental redundancy, additional parity bits are transmitted in each retransmission term. So these are the three type of HARC. HARC is almost being implemented in almost in all next generation wireless networks. Yeah, but in the background, you need to keep one thing in mind. When I say HARC is more efficient in terms of reducing retransmissions, in terms of recovering packet, it is not coming free. It is coming at the cost of complex hardware, obviously, that you need to, combine those copies. And extended memory requirement, as pointed out by in the recent session, that once you need to buffer those copies, you need to, you should have large memory requirement. And yeah, okay. So those were, requirements for HARC. Now, this is what we have discussed, that in FDMA, how the transmission happens. Since they are on different frequency bands, you can keep on transmitting independently a fresh packet whenever it is lost in the previous cycle. In NOMA, since it is SIC based, if you stuck at SIC, you can't comment on the second packet also. Now here they discuss actually, because it may always happen that once you stuck at SIC, if I provide you the first copy of the packet, that is the new S1 transmission copy, it may be possible that when you combine the retransmitted copy with the earlier copy, you may be able to decode S1, you perform SIC, and then decode S2. But it may also be happening that given the channel condition, even though you are not able to decode S1, you have decoded something, maybe with BR 10 raised to power minus 3 or 4, depending on the application requirement. You still perform SIC and you are still able to decode S2. But that all depends on the channel condition, your transmitted power, your interference level, your circuit efficiency. So those are all possibility. Having said that, you perform SIC and you stuck at packet 1, the packet 2 cannot be decoded. It is just one possibility out of many. So there are many possibilities that it may be possible that S2 may be recovered without retransmission required, just by retransmitting S1, decode S1, remove it from the complete received signal, and then decode S2. It might be possible that even after that S2 is not able, you are not able to decode S2. In that case, you need to ask the transmitter for another copy. So all those are possibilities that they have discussed in paper. And this is the RSMA retransmission. This we discussed in detail, that just by transmitting S11, that is a part of user 1 signal, you actually can make the SIC running rather than sending the complete packet of user 1, right? Then, so here in detail, they have discussed those, whether S11, so when there are 3 copies, S11, S12, and S2, you receive, then there are 3 decoding orders. What we discussed, decoding order 1, 1, 2, 1, 2, decoding order 2, 1, 1, 1, 2, 2, or decoding order 3, 2, 1, 1, 1, 2. Why they have chosen this particular decoding order that we discussed? Because in literature, they have shown that out of the 3 decoding orders, this is actually a more efficient decoding order or capacity achieving. So that's how they have taken this decoding order 1 into the discussion. Now, this is again very important assumption, and more or less every theoretical work based on certain assumptions which do not hold in practical world, right? So like they have assumed here, one is obviously the perfect synchronization, that whenever the packets are superimposed or packets are received at the receiver, they are perfectly aligned. But in real time, because of the oscillator drift, because of the LNA problems, because of clock drift, the reception is not perfect. There is always a synchronization. This is quite similar to, in timetable, whenever we start the session and we say, fine, class will start from 9 to 9:50. It is designed like everyone will come at 9 and we will finish the class at 9:50. But it doesn't happen in real world. Somebody will come at 9:01, somebody will come at 9:02, 9:05. They keep coming asynchronously. It's the responsibility of the receiver or the processor or the teacher to manage this asynchronous reception, that probably initial 5 minutes you should not cover the crucial part, so that even if somebody misses, it doesn't harm, right? So in practice, everything is asynchronous. Nothing is completely synchronized. So, and other assumption what they assume is that two user has the same service requirement. That is, in the mathematical framework they have discussed. When we talk about outage probability or BER, so outage is defined that your rate is supported with the rate what channel is supporting. So there actually that rate requirement is coming, and here they assume that that requirement is same for both service. Some particular service both the users are looking. So that actually adds some simplicity in the mathematical analysis. Some closed forms are tractable now. Otherwise, if we do not introduce these, still framework can be propagated, but then system becomes more complex. Then well, okay, this we discussed that weak user need to provide more power. Sometimes again, another the important part of any paper is the system model. Whenever I go through any paper, I make sure that system model is very much clear, because unless you are clear where you are applying the idea or what is the scenario, how many antennas are there, what is the distance, what modulation scheme you are using, because whatever results we are giving, whatever discussion we are doing, they are based on a certain assumption. Once you move from BPSK to 16 QAM, probably the performance of system will be entirely different, because the constellation points are different. BPSK is more robust to noise. QAM is not. So if channel is more noisy, probably your 64 QAM or 256 QAM will not perform better, because points are very much dense in the constellation plan, right? So whole discussion will take a new route if I change the modulation scheme, if I change the channel requirement, if I change the, so here we assume that H1 is greater than H2 so that we can perform the SIC. Practically channels are very dynamic. They change here and there. So probably you need to go for some kind of weighted outage probability in practical scenario, right? So the system model is that there are two users with single antenna and a common base station with one single antenna. Here, if you, so essentially it is combination of multiple CISO links. You can say, we cannot say it as MISO, because typically MISO is defined for the two users where in uplink where one user having multiple antennas. Here, if you see, each user is having single antenna, but here, if you see, it looks like two users are coming. So I believe more appropriate word will be sort of multi-user MISO, right? Where there are multiple users, but each user is having, but though these definitions keep on changing author to author, some authors use a different word for this scenario. So make sure, like the definition of throughput, different users, different authors define it differently. So it makes sure that when you go through a paper, what is, or whenever you are going through the performance metric, you make sure how the author is defining. Sometimes we just say throughput, and it is fine that whatever number of bits we are receiving in a given time slot. Sometimes they define good put. There they remove those training bits or those preamble part and that actual data rate. But loosely, sometimes authors use the same term for both. So make sure that you clear what term they are using. Successful copy will be buffered. Okay. Yeah, this is another important assumption, that we assume that user do not have CSI while base station has perfect CSI. And how the base station will acquire that CSI, this paper talks about. When the user sends the request for, because often this question comes into mind, that how user will come to know, or that which user need to split. It's a distributed system. So here they talk about that when user sends a connection request to the base station that I wanted to join your group, then through that message, base station can estimate the channel, and then that information it can convey back to the users. This is what it said. When the user send the request for connection, base station can obtain the CSI for users and decide who will split the user. Because once base station has the CSI, I know which one is high, which one is less. I will communicate the higher channel user that you split, the other will send the non-split one. That's how this is what it talks. These equations we have discussed, the summation of PIs and all. Okay, this is what SIC discussion that is. So the mathematical part I'm not discussing. This we have discussed. Now these are the figures. That's what I have included in the slides. That so they have discussed in detail how the also they have thrown some light on the fact that the power allocation factor need to be designed very optimally, because that decides whether SIC will stop, how many transmissions are required, whose packet will fail. And here now they discuss that if you split into more number of packets, actually your SIC will not stop. So essentially you are avoiding retransmissions. They have also discussed the other part, which though we skipped, that even if you split in more number of packets, then looking at this, it looks, then it is again better. But see, just keep on adding certain stuff doesn't help. Maybe those who have seen the selection combining, they know that the curve of selection combining is, if you have the expression, the mathematical expression of gain in selection combining contains L. That is the number of antennas, the independent paths. It looks like larger the number of independent paths, I mean the number of antennas, your performance will increase, but your differential gain will decrease. Why? Because when you increase number of antenna, when there is one antenna, you have one path. When you have two antennas, you have two paths, independent paths. You have three antenna, you have three paths. But when you increase the number of antenna, channel becomes correlated. So your independency across path goes. And once information is not independent, it has less content, right? It's like this. The earlier session was more information, had more information. Now this session has, the differential gain is less. Why? Because I have already covered that part there. So in a way, though it is another session, but it is not having an independent information. That's how the gain is not more. The same happens in the number of antennas, that when you increasing at a large number, your independent paths die out actually. This could handle collision better, but it will introduce more complexity and user. But then they have, again, nothing comes free. When you split in more, your complexity increases more. Your algorithm need to be designed in more perfect way, that how many parts need to be in how many numbers you need to split. So all those things are there always, but there is an optimum number in which it can split. Then here they have discussed again some more cases. What if this fails? What if this doesn't fail? Then you need to ask for S2 retransmission also and all. So this is what they have discussed. While Deepak is sitting here, he may be thinking, sir, jaldi khatam kariye, mera bhi session hai, otherwise late ho jayega. Then there were few interesting, maybe in case if any of you got interested in this and go through this paper. While I was discussing this paper with my scholar, we got certain facts that we were not able to understand. I don't know whether authors also have made that mistake, or they had some different view of that which they have not discussed into the paper. Because when they say, let's say when SIC is being performed, so once first signal will be decoded and then you go to the second. So if you mathematically calculate the error probability of second, there are two possibilities in which this packet will be error. Packet 1 itself is not decoded, plus packet 1 is decoded but second fail. So in that chain fashion we write the probability equations. But when they define the probability, it seems that they just talk about the post SIC error. So there is nothing wrong in defining post SIC, but somehow we couldn't get any impression from their theoretical expression that they are considering the post SIC only, though their mathematical expression says. But we were simulating this paper and we're trying to see what is the actual scenario that they have discussed. So there in different results they show that if you compare the error probability with respect to rate, that how the RSMA performance is better than NOMA or FDMA. Under certain scenario, there may be cross points, which shows that actually till this rate, this is better. Say, for example, if you see, if my rate is somewhere around 2.8 to 3, probably FDMA user 2 error probability is high, right? RSMA user 1 is always better, but RSMA user 2 may have bit high error probability in low rate reason. So if you have 1 to 1.2 around, actually NOMA user 1 is performing better. So that curve practically gives you idea that in which rate region you are operating. Accordingly, you choose the best. There is no global best. Everything is best in a certain scenario only, right? See the Vaibhav Suryavanshi. He may be the best in T20, but not performing currently in England, right? Then, yeah, these are some more curves where they have compared RSMA, NOMA, and FDMA. And then these are appendices where they have actually discussed the, given the proof of those mathematical algorithms. So the paper primarily based on the fact that we have discussed during slides that splitting actually helps in avoiding retransmissions. That's the summary of this paper, right? I think I'll stop here, right? Thank you. Any question related to that in case? Maybe Deepak can comment if you are receiving some patent applications on RSMA. Okay, application. That's good. I mean, people are, because once patent will come, then companies will try to implement it. It will come into market. It will standardize. It's a long way, but it's good that people are trying to implement it at hardware level.
College of Engineering.
अरे कोई फोटो भी तो लो भाई. Thank you. मैडम ये जाएगा कैसे?
सर आप हमारे डिपार्टमेंट में ही लगा के जाए.
हाँ वो that's better option. हाँ प्लीज प्लीज. हाँ हाँ
जो होता है सबका यूजर
हाँ.
सब क्या है या कुछ शॉर्टकट.
चैट जीपीटी के जमाने में शॉर्टकट ही शॉर्टकट है. वो तो ट्रू है, वो ट्रू है. दैट्स एडिंग हेल्प ओनली. वो तो मैथ तो थोड़ी आपको करनी पड़ेगी. देयर इज नो शॉर्टकट.
बट वैसे चैट तो बेनिफिट मिल रहा है.
मुझे तो बहुत मिलता है. इट एटलीस्ट गिव्स यू डिफरेंट डायमेंशंस ऑफ थिंकिंग. सी वी हैव अ लिमिटेड थिंकिंग. या तो आप भी उतना लिटरेचर पढ़ो, 60 साल बाद आप भी वही थॉट दोगे जो चैट जीपीटी दे रहा है. बट अभी विद दिस लिमिटेड नॉलेज इट गिव्स यू मेनी डायमेंशंस टू थिंक. अच्छा ऐसे भी हो सकता है. दैट्स द ब्यूटी. तो ये एक बहुत ओल्ड सेइंग है, नो, साइंस इज अ गुड सर्वेंट बट अ बैड मास्टर. तो चैट जीपीटी